So we're going to go over a couple things that we did in probability. Just kind of the formulas, a couple of little detail things that will be covered on the final. So the first thing we talked about was just the symbols, and I'm going to make this a little smaller so we can see everything at once. There we go. The symbols and outcomes and things like that. So if you look at the first one, we have a chart of people, the activities they like, and then who they are. So right now we're just listing outcomes. So it says the outcomes of people who like SW, which is swimming or biking. So anybody who falls in the swimming or biking category, so that would be Tina. She happens to have both. But remember, or means one or the other. Jordan falls into biking, so he's good. And Alexis falls into swimming. And then they're the only three. So that means those outcomes, remember we want brackets, would be Tina, Jordan, and Alexis. Okay. So then, when we go back to do the next one, I'm going to get rid of these highlights from the first one. The next one says SB is for softball, but it's saying not softball. That's what the line on top. So anybody who doesn't like softball, so that's pretty easy to see without highlighting that that is Tina and Katie. Both do not like softball. Everybody else does. The last one is, I'm going to use a highlighter for that one. It's running and basketball. Okay, so anybody who likes running and basketball, but then not that. Well, if you look, the only person who likes running and basketball, sorry, Cody, that was a highlighter, is Anthony. So that means the people who don't is everybody else. So that's Tina, Katie, Jesse. Oh, there's the highlighter. Okay. Jordan and Alexis. Okay. So that's just naming. The other questions you could get asked are like, how many people like this, whatever, but you're still analyzing who likes what. Okay. So then we went through a couple different formulas. Okay. There were 3 big formulas that we used throughout the chapter. The first one was the independence rule, which we also used for multiplication. Okay. So that is the probability of A and B is the probability of A times the probability of B. Okay, so that was a big formula that we used throughout the chapter. And the keywords that you want to look for there are and, because of the and symbol, and obviously independent. The addition rule, that one was a little longer. That's the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. Okay, the big word there is or. Okay. Now remember, if the problem said that if there was an or in the problem and it was independent, that's where you can switch this out for that, but that's only if it states clearly that they're independent. The last one that we talked about was conditional probability. That was the probability of A given B equals the probability of A and B all over the probability of B. You guys, conditional probability, remember that's when you narrow down your sample space. Keywords there were 3 of them. Given was a big one. If was a big one. And also was a word as well. Okay. So I'm going to work through a couple problems here and talk about when to use what and just how they are applied in each different type of situation. So this one says Genoa High School has 529 juniors. Of the junior class, 378 students are involved in a sport, and 209 are involved in a sport and have a job. So there's a key word there. Assume that having a job and playing in a sport are independent events. Okay, so there's something else that's important. What is the probability that a randomly selected junior has a job? Okay, so I always write out what I need. I'm looking for the probability of a job. Okay. Junior doesn't come into play here because everybody's a junior, so it doesn't have an effect on probability. Then what do I know? I know the probability of playing a sport is 378 out of 529. And the probability of playing in a sport and having a job is 209 out of 529. All right. So then it says assume that they're independent events. So because we can assume they're independent events here, you guys, I can use this formula here. So the probability of a sport and a job equals the probability of a sport times the probability of a job. Okay. So this is 209 out of 529. The probability of a sport is 378 out of 529. And I am looking for the probability of a job. So what that means is I'm going to take that 209 divided by 529 and I am going to divide it by 378 divided by 529. So that means the probability of a student having a job is about 55.29%. Okay. All right. For the next one, it says the only 11th grade physical education courses are weight training and team sports. There are 500 11th grade students. Based on the data that follows, what is the probability that a randomly chosen student is taking weight training and team sports? So I am looking for the probability, oh, that's a terrible P, let's try that again. The probability of weight training and team sports, that's the goal. Sorry, I don't know why, my computer just hates me. That's like the theme. That's not a specific day, it's every day. Okay, so what are we given? 140 students are taking weight training, so that means the probability of weight training is 140 out of 500. The probability of team sports is 175 out of 500. And the probability of weight training or team sports. Okay. Let's see here. Equals. Yeah, I know you're going to do that to me. It's 280 out of 500. Okay, so now we have all of our information down. So you guys, some keywords here are or, that's a big one, and. Okay. As soon as you see or, you have to default to the addition rule. So if you look, we have everything we need for the addition rule. So the probability of weight training or team sports is the probability of weight training plus the probability of team sports minus the probability of weight training and team sports. That's the formula. So the or probability is 280 out of 500. The weight training is 140 out of 500. Team sports is 175 out of 500. And I am looking for the unknown. Okay, the and. So in my calculator, I'm going to add together 140 out of 500 and 175 out of 500. Okay, so then I have 280 out of 500 minus that answer, which means I am at negative 0.07. So remember, that's negative 0.07 equals negative x. So when you divide both sides by -1, you'll get a positive. So it is a 7% chance. And that isn't rounded, that's exact. Okay. All right. For the next one, okay, now we're moving on to what independence means. So it says, Ben owns a delicatessen. He collected data on sales for his most popular sandwiches for 1 week and recorded it in the table below. I went through and I filled out the entire table for you with the totals just so we didn't have to waste time doing that. But just remember, if that's blank on the final, you're going to have to find the totals yourself. It says each of the following statements describes a pair of events. For each statement, determine if they're independent based on the data in the table and write an explanation. So you guys, that's when we're using the independence rule from the first page. And we are determining if it's a true statement. And remember, you have a 1% swing here. If it's within 1%, then we say they're independent because we have such a large sample space. So a random customer orders Ben's Club sandwich on country white bread. So that's saying the probability of a club and country white bread is equal to the probability of a club times the probability of country white bread. Okay, so they're just seeing if there's some sort of correlation between those two. So now you look at the table. The probability of having a club and country white, well, 44 people order Ben's Club on country white bread. So 44 out of the total 320. Okay. The probability of a club sandwich, just in general, is 92 out of 320. And the probability of country white is 102 out of 320. So, if you put that in your calculator, I'm just going to do it over here. I already did it, so I'm just going to give you the answers. I'm sure you guys are capable of putting that in your calculator. You get approximately 13.75% over here. And then, that should be a percent. Oh, for the love. Okay. There we go. And we're back and running, maybe. We're clicking on everything. Okay. Seriously. All right, and then if you multiply these together, you get about 9.61, or 16%, excuse me. All right, so that is not a 1% swing, which means these are dependent. All right, so what does that really mean? That means that a customer ordering a club sandwich does have an effect. They're dependent on each other. So a customer ordering a club sandwich does have an effect on the probability that they'll get country white bread. Okay, so a customer ordering, sorry, my handwriting sucks, a club sandwich does affect the probability that they order country white bread. All right, so if you think about it, this is important because people like to know if I'm running a business, right? What should I order? What's correlated together? So that's kind of what this is doing. This is saying, if you look at that data right there, out of the people who ordered club sandwiches, it is overwhelmingly more likely that they get country white, 44 compared to 24 and 24. So that makes sense that one depends on the other. Okay. So for the next one, now we're going to compare roasted chicken and whole wheat bread. So same idea. Okay. The probability, I'm going to use RC for roasted chicken and whole wheat bread is the probability of roasted chicken times the probability of whole wheat bread. Okay. So we have we're getting rid of all this. Let's see if it'll let me this time. There we go. The probability of roasted chicken and whole wheat bread is 26. And then the probability of roasted chicken in general is the 75, and whole wheat in general is the 112. So those are the numbers we're going to use here. I'm going to shrink this down just for a second so I can get it all on one screen. So the probability of both was 26 out of 320. The probability of roasted chicken is 75 out of 320. And the probability of whole wheat is 112 out of 320. Okay. So when you work those out in your calculator, you end up getting 8.125% over here is equal to about 8.2% over here. So because these are within 1%, we would say yes, they are independent of each other. Okay, that means because they are independent, a customer ordering a roasted chicken sandwich, I'm going to shorthand it here just for time's sake, does not affect the probability what is going on with me? I don't even know if that's spelled right, sorry guys. Does not affect the probability of ordering whole wheat bread. That's literally the sloppiest thing I've ever written, so sorry. Okay, so if you look at the data, the roasted chicken sandwich, see how it's even across the board? 25, 26, 24. So it's not saying, oh, if they ordered roasted chicken, it's pretty likely that they're going to order this type of bread. Okay? If you look at the Veggie Delight, for instance, I would take a guess that if you're looking at Country White, right, see how that's overwhelmingly different than whole wheat and sourdough. So the one thing you might be able to say is, oh, well, looking at this data, if they order a Veggie Delight, they probably are less likely to get the Country White bread. So stuff like that. That's what this all means. Okay. On the final, we'll just ask for independent and dependent. So just have a pretty good understanding of what that means. All right. On the last page, we're going to talk about one more word problem, and then I'm going to go through just some general probability questions to make sure we get everything covered. This says last year at all technical high school, 20% of the students received an academic award. That same year, 16% of the students received an academic award and a service award. Okay, so got a keyword in there. What is the probability that a student received a service award given, okay, that's conditional probability, they received an academic award? All right, so we are looking for the probability that they got a service award, knowing or given that they got an academic award. That's what we're looking for. It says that 20%, so the probability of an academic award is 20%, so 0.2. And the probability of both an academic award and a service award is 16%, so 0.16. All right, so because of the given here, that's conditional probability. So we're looking at the probability of a service award given an academic award is the probability of both a service award and academic award, doesn't matter the order, all over the probability of an academic award. So in our case, we are looking for this. So we have x equals 0.16 divided by 0.20. If you throw that in your calculator, you end up with 0.8, which is 80%. That's your final answer. Okay. All right, the last thing I'm going to go through is just some basic probability. Again, I filled in this table for you to make life easy. If the totals aren't there, make sure that you fill them in. So we are looking at 3 different age ranges, 18 to 23, 24 to 34, and 34 plus. I guess that should technically be 35 plus, but whatever. And then 3 different types of activities they like to do on vacation: beach, hiking, and sightseeing. All right, first one says, what is the probability of randomly selecting a person who was between the ages of 24 and 34 and likes to sightsee? So we want both happening. So 24 and 40 to 34 and likes to sightsee is 33. So that is 33 out of 321. Sorry, still thinking the last problem, 321. So that should be about 10.28% when you throw that in your calculator. Okay. The next one, what is the probability of randomly selecting a person who is 34 plus if they like hiking? Okay, this is conditional. So this is my sample space, the people who like hiking, which is 88. Okay. Out of those 88 people, how many are 34 plus? That is 24. So 24 out of 88 is about 27.27%. Okay. C, what is the probability of randomly selecting 2 people who like the beach? Okay, 2 people who like the beach. 137 people like the beach out of 321. Well, if you pick the first one, they're not available to pick again. So if you're selecting 2 people, this is where you have to take down and say now there's only 136 people who still like the beach out of 320 people who are left. So if you're selecting more than one, you got to change that sample space because they are no longer in it. So that is about 18.14%. You guys, obviously, I would be putting these in my calculator if I were you, as I go to make sure that you're good to go on the calculator part of it. Part D, what is the probability of randomly selecting 2 people who like to sightsee given their ages 24 to 34? 2 things going on here, guys. Given, we have conditional probability, so we're going to slim down that sample space, and we're picking 2. So first, let's figure out our sample space. Given their ages 24 to 34, that is 126 people. So out of those 126, how many of them like to sightsee? That is 33. Okay, but if I'm picking 2, that's when you got to take one down. You pick somebody, they're out of the running, you can't pick them again, so there's 32 left out of 125. Okay, so the probability there is about 6.70. All right, last couple. What is the probability of randomly selecting a person who is in the youngest age group and likes to hike? Okay, so the youngest age group is obviously this guy right here, 18 to 23, and likes to hike. So 18 to 23 that like to hike, that is 15 out of, now we're selecting out of the whole total, that's 321. You don't change that unless you have a given, right? We only changed it in B and D because it was conditional probability, so we were changing our sample space. So this is about 4.67%. Okay. All right, last but not least, we have what is the probability of randomly selecting a person who likes to go to the beach? All right, this is just general, the probability of liking to go to the beach. So that is 137 out of the 321 total. So it is about 42.68%. So that makes sense because that's the highest number out of everybody. Because who doesn't like to go to the beach, right? All right, so that is Unit 4 in a nutshell. Make sure you work through the review packet. If you have any questions, let us know.